Morning, everyone. I made a couple of different videos, mostly because I couldn't figure out how to do a PowerPoint presentation merge into an existing video that I had written out. So I've got two parts. I think you can figure it out. This is just a short little section of things that I thought were kind of important from this little 3-page section in your textbook, 680 to 682. And so it expands upon the arsenal of ways that people figure out kinetic information from going into the lab and doing experiments. So I have here, I'm sure you recall something that technically is called the method of initial rates to determine order. That's the technique that involves changing the concentration of only one reactant to see how the rate is affected. We talked about one yesterday, if you recall, that had a half order. Most of the ones you see are either 0, first, or second order. Depending on the reaction, this could be pretty time consuming, and you would have to run many trials of several reactions. There's a more efficient technique that's called the isolation method. Here, all the reactants except one are present in very large excess. For example, consider a reaction that has a rate law that's first order in A and second order in B. If you ran this reaction with B in very large excess, you can get out useful information by making the assumption that whatever the B concentration is what it was originally. Because if it's in such large excess, the total amount is changing very small amounts over time. And so effectively, your rate law greatly simplifies to a rate constant times the dependence of A. And you could do your standard techniques to prove, let's say, first order or whatever. Here I have first order, so you'd see a linear relationship, for example, between the natural log of concentration and 1 over time. The rate constant, though, that you would get from the slope is really equal to the actual rate constant times that original concentration of B squared. Therefore, we don't call it the rate constant, we call it the effective rate constant. This process that I just explained is called a pseudo first order reaction. It's first order in A, but the overall reaction technically is a third order reaction, but you've kind of swamped out the effect of B by having it such a large concentration. Of course, you could do exactly the opposite. Run the reaction with A in large excess, and the original rate law would simplify to an effective rate constant times the concentration of B squared. And you would see the appropriate linear relationship for that, for a second order expression, where you would plot 1 over the concentration versus T. This is called then a pseudo second order reaction. This is often seen in reactions that occur in an aqueous solution. They could mistakenly be reported as first or second order in the reagent, but they're actually pseudo first or second order because water might actually end up being one of the reactants. If it participates in the reaction and it's the solvent, the water's in such large excess that you're not going to really see evidence of it changing over time. And I just have a little example here I stole from our book. It turns out that the hydrolysis of acetyl chloride reacts with water, and it looks like it's an overall first order reaction. It's really a second order reaction. It's first order in the acetyl chloride and first order in water. Recall that when you have water as your solvent and it's the acetyl chloride is a relatively small amount, the numbers they say here, if the acetyl chloride is 1 molar or less, and the water concentration then is about 55 moles per liter. This would qualify as a pseudo first order reaction. Now, it is possible to measure the actual K value accurately. You would need to run the reaction in a way with different concentrations of water. I'm a little unsure about how you would do that. Perhaps if you ran the acetyl chloride at a very high concentration, you could create a situation where the water wouldn't be 55. That's what I'm thinking. But if you did that, if you had a variety of different water concentrations, then a plot of the effective rate constant times the concentration of water would yield a plot with a line of slope equal to k. Essentially, this equation would extract the real k value. So I don't have much more on this. I noticed there were no problems at the end of the chapter that had to do with pseudo or first or second order reactions, but this is just kind of a descriptive thing I might ask you a multiple choice question on. So now at this point, please go to the March 21st Part 2 video. See you there.